Okay, great. That looks like everybody who was here yesterday is back again this morning. So let's make a start. So this morning I'm going to talk about combining MPI and OpenMP. So what I'm going to cover is a bit of motivation. Why would you want to do this? And then move on to look at the potential advantages. What might you hope to gain by moving from, well, typically moving from a pure MPI code to a mixed MPI and OpenMP code. And I'll talk about some of the problems that you're likely to encounter, some of the things that can go wrong with performance and portability. And then we'll look at some of the technical details of the different styles of how you can write MPI and OpenMP programs, and talk a little bit about MPI's thread interface along the way. So again, as per yesterday, please feel free to chip in with questions in the chat window as we go along. Okay, so motivation. Why do this? Why would you want to do mixed MPI and OpenMP? Okay, so it's just because of the type of systems we have. We've got multi-core chips everywhere. Almost all current CPU systems are clustered architectures, so they're distributed memory systems where each node consists of a shared memory multiprocessor. So might have actually typically two chips, two sockets in a node these days. Seems to be the favorite number on current systems. But nevertheless, you've got a single address space within each node, but separate nodes have got separate address spaces. So the question is, how should we program machines like this? Well, it's clearly perfectly possible just to use MPI across the whole system. So just run essentially one MPI process per core on every node, and the MPI library is libraries are set up so that they have efficient means of communicating between processes on the same node via the shared memory. So what's the problem? Okay. Well, in general, of course, we can't use OpenMP or threads across the whole system because that would require support for a single address space. It's not completely impossible. People have tried in the past to do software support for a single address space across distributed memory systems. It's never really worked very well. It's very hard to do it efficiently. It's also possible, and you don't see many machines like this these days. It's been done in the past, where you use hardware support to do it, but that turns out to be an expensive solution, and it still doesn't scale up to the hundreds of thousands of cores that we're seeing in machines today. So the other option is say, okay, we could use OpenMP or some other threading interface within a node, and then MPI to communicate between nodes. And the question is there any advantage to doing that? What are the potential advantages of doing that? Okay. Well, we should at least temper our expectations here, because in general, going from MPI, pure MPI to MPI plus OpenMP will not improve performance, and may actually make things worse in the regime where your MPI application is scaling well. Okay, so if your MPI is doing fine up to the up to the number of nodes or cores that you're interested in running in, then you're very unlikely to get any benefit from adding OpenMP. The benefits tend to come where the MPI scalability, so that could be either in time or in memory usage, starts to run out. And using MPI and OpenMP together may allow you to extend the scalability to larger core counts. So this is sort of the typical performance curves that you might expect to see. Okay, so just without putting any numbers on it, if I sort of sketch the performance of the code, so high is good against the number of cores that we're using, then you might see something like this for the red line for your pure MPI code. Okay, so it starts off scaling quite well, so you get almost linear scaling. Then after a while, the scaling tails off. The performance reaches a maximum somewhere, and then if you try to use more cores, more MPI processes, the overheads of communication and load imbalance and so on start to dominate, and the performance starts to drop eventually. What you will typically often find if you go to MPI and OpenMP is that, say for low numbers of cores, you may actually find that the performance is worse. Because it adds some additional overheads, but the scalability extends further. So after a while, after a certain number of cores, there's a crossover point, and the MPI plus OpenMP version starts to perform better, and it has a higher peak performance at some higher core count than the pure MPI version. Before it too eventually will the performance will turn over and start to get worse again. So that's kind of what you're expecting. So if you're operating in if you're running your application code in this regime out here, where the MPI performance is tailing off, then you might hope to get some boost from using combined MPI and OpenMP. If you're operating in this regime down here, where the pure MPI code is scaling just fine, then you might not do so well. Okay, so what are the potential advantages of combining MPI and OpenMP? So I'm just listing them here. I'm going to go through them all in a bit more detail. So the things we might expect to gain are reducing memory usage, exploiting or more easily exploiting additional levels of parallelism, reducing load imbalance, avoiding some replicated computation, and reducing communication costs. So let's look at memory usage first. So some MPI codes use some replicated data strategy where all your MPI processes have a copy of some major data structure. Even if we just do classical domain decomposition codes, there's a certain amount of replication going on if we have halo cells or ghost cells to easily manage domain decomposition and halo swapping. And the MPI library can internally consume significant amounts of memory because it has to allocate some memory for message buffers. So whenever have these replicated data structures, a pure MPI code needs a copy of these things, whatever they are, per process and therefore per core. Whereas in principle, a mixed MPI and OpenMP code might only require one copy per node. Okay? And then that data structure can be shared by multiple threads within a process. And it will also reduce the amount of the number of MPI or the number of MPI buffers required, because those buffers which are used to send intranode messages, so messages between MPI processes running on the same node via shared memory, typically also consume some buffers space. Those will no longer be required. Okay, so I think it's already an important technique. It's probably likely to become increasingly so, partly because the way we see machines going, the amount of memory per core is not likely to increase very much in the future. And so although we're going to get systems, we'll carry on getting systems with more cores, particularly more cores per node. So that's the main way that systems are growing at the moment, is then we're not really seeing big increases in the number of nodes. Most of the increase in performance comes from having more cores per node, and therefore it's although it's perfectly possible to put a lot more memory on a node than what we typically see, it's expensive and consumes a lot of power. So there are limits to how much memory you can put in to a node practically, and so the amount of the memory per core is not really likely to go up anytime soon. Okay, so just to illustrate the effects of domain size on Halo storage, typically, using more processors implies a smaller domain size per processor. Okay, unless you have a problem that can genuinely weak scale. Okay, in practice, the use of most applications on large machines is kind of neither pure strong scaling, where you're just interested in a fixed problem size and trying to get faster execution times by adding more cores, nor is it pure weak scaling, where you are basically have where your problem size per core remains constant and you increase the problem size by adding more cores. Most applications in practice are used in a mode which is somewhere in between. However, so even though the amount of Halo data does decrease as the local domain size decreases, it eventually starts to occupy a significant fraction of the storage, and that gets even worse if we have, say, deep halos, so more than one layer of Halo cells around the domain, or problems like quantum chromodynamics, where you're operating in 4 or 5 dimensions instead of 3. So just to put some numbers on that, suppose we have a problem where the local domain size per process is 50 cubed. Okay, and so in order to store the halos, we actually need a domain of size 52 cubed. Okay, so we need an extra face on either side of the cube to just store our Halo data. Then the amount of data in the halos accounts for about 11% of the that memory. But then as we shrink, okay, if we go down to 20 cubed, then that goes up to 25% of your data in your halos. And if you go down to 10 cubed as your local problem size, then you're getting towards 50% of your memory usage is actually in Halo storage. So even if you're not doing any sort of replicated data, just the data that goes into Halos can become important. So that's actually one of the simply just saving memory or being able to fit a certain problem into memory is a consideration for a lot of codes, and it's the sole motivation in some cases for doing hybrid MPI and OpenMP, and the performance is essentially a secondary consideration. So the other way of thinking about that is say, well, okay, if I need some extra memory, what I could do is simply run fewer MPI processes than cores to underpopulate my system, so that every MPI process has access to more memory. But then you are leaving some cores idle doing nothing. So then you might think, okay, well, actually, I may as well try to exploit those extra cores if I use threads rather than MPI processes to occupy those idle cores. then I can probably do so without adding to the memory usage of the code. So you think of it, okay, your prime motivation is memory. You want to underpopulate with respect to MPI processes, but you can recover some of that lost performance from having idle cores by using OpenMP within a process, and that's probably not going to increase the, or hopefully that's not going to increase the memory usage very much. Okay, so let's move on to some more performance-based considerations. Next one is the ability to exploit additional levels of parallelism. Okay, so some MPI codes are not going to scale beyond a certain core count because they run out of available parallelism at the outermost level, and that amount of parallelism may well be constrained by the problem, the physical problem that you're trying to solve. However, there might be some additional lower levels of parallelism that could potentially be exploited. And in principle, there's no reason why you could not also do that with MPI. It's just in practice that might be hard or not very feasible because several reasons. The lower level of parallelism may not be so convenient for distributed memory. It might be hard to load balance, or it might have some irregular or runtime determined communication patterns, which are very difficult to implement efficiently with MPI, but can be done relatively easily with OpenMP. On the other hand, it may just be down to software engineering concerns. It might just be really hard to work around the design decisions that were made in the original MPI version in order to exploit additional levels of parallelism. So it might, just simply the amount of work you'd need to do to the code to exploit that extra parallelism using MPI might just be infeasible or intractable, or you don't have the programmer resources to do it. But doing it with OpenMP might be more more tractable and be doable in less time with less effort. Yeah, so may for practical reasons be easier to exploit that additional level of parallelism using OpenMP threads. So you can take a fairly straightforward approach. You can take an incremental approach by doing one OpenMP loop, adding OpenMP to one loop at a time. That might not be performance optimal, but at least it would maybe keep your development cost, development time to a minimum. So obviously the OpenMP parallelism can't extend beyond a single node, but that might be enough. Okay, so we're seeing systems with quite a lot of cores per node now, so that gives us potentially quite a lot of opportunity to exploit a reasonable amount of parallelism at some lower level using OpenMP. Okay, so next one is avoiding replicated computation. So if, some MPI application codes will replicate some computations because on every process, because that might be cheaper or just easier than computing on one process and communicating the result to all the others. And so, for example, sometimes it's possible to trade off duplicated computation in halo regions with communication. And so you can do things like, okay, you can exchange deeper halos. If you exchange a 2 deep halo, you do it every 2 time steps. So you reduce your communication frequency, but that means you have to replicate some computation on the intermediate time step in the halo regions between the neighboring processes. So that's kind of one scenario where this kind of things happens. There are plenty of others. So your mixed MPI and OpenMP may reduce that. So for example, if you have less data in halo regions by having larger domains, that means that implies less replicated computation, for example. Next one would be reducing load imbalance. So if you have a problem that is not naturally well load balanced, then load balancing between MPI processes can be hard because you need to transfer both computational tasks and their associated data from overloaded to underloaded processes. So that means that transferring small computational tasks might not be very beneficial, because the cost of moving the data might outweigh any gains you get from improved load balance. It's also, if you try to scale to very large numbers of processes, it may be trying to have do load balancing where actually where you want a global view of all the loads. So some process knows something about the load on all the different processes to try and decide which are overloaded, which are underloaded, and which are going to, where the communication is going to happen to try and balance the load. Eventually, that's that kind of thing may not scale very well. So you might end up having some sort of compromise where, for example, you restrict yourself to transferring loads only between neighboring processes in whatever the natural topology is. So if you have a classic domain decomposition problem, you might consider only transferring load between processes which would naturally communicate with each other anyway. But that might, so that'll be less costly, but it might not solve the load balance problem so effectively. On the other hand, load balancing between threads is much easier because really, in principle, we only need to transfer tasks and not the data. So the overhead's typically much lower. So fine-grained load balancing is more feasible with threads than it is with processors, and it's easier to have because of the shared memory. It's easier to have a global view, at least across the threads, in a process of which ones are overloaded and which ones are underloaded. But you might even not even care about that, because you can just do it's very easy to do dynamic load balancing between threads, whereas dynamic load balancing between MPI processes is quite awkward and painful to do. So what does that mean? Well, it means with application with load balance problems, keeping the number of MPI processes smaller may be an advantage. So, for example, it might be if I'm running on, say, let's pick some nice round numbers. Suppose I'm trying to run on 10,000 cores. Okay, so load balancing 10,000 MPI processes may be quite difficult, but is it okay? So say maybe it would be better to try and load balance 1,000 MPI processes and then have 10 threads running per process, and do the load balancing locally between threads inside each process. About reducing communication costs. So kind of maybe your first thought about hybrid MPI and OpenMP is that, well, yeah, obviously it's going to reduce the communication costs because communicated data inside a node is going to be faster between OpenMP threads than it is between MPI processes, because there's no intermediate buffer copies required, and there's no overheads of calling into the MPI library. So that is true to some extent, but there's lots of caveats, and we'll come back to that later. Okay, and in practice, that might not be the most important consideration for a lot of codes. However, in some cases, MPI codes communicate more data than is actually required, and this happens where the actual data dependencies are irregular, or they are data dependent. Okay, so they, whether your neighboring process really needs this value depends on the value of the data. Okay, so things like it depends on the position of a particle. Okay, does my neighboring process really need this? Well, it depends on where this particle is, and don't necessarily know. Okay, so in order to make implementation easier, a lot of MPI codes end up communicating data that's never actually used on the recipient process. Okay, and in some also with collective communication, in some circumstances, collective communications can be improved by using MPI and OpenMP. So, for example, for operations like all reduce or all to all, actually a bit more can be a bit more efficient. In principle, your MPI implementation ought to be well optimized for the architecture, but that's not always the case. It's actually quite difficult to optimize the MPI implementation for all possible cases, because you've got to cover you've got to cover ranges of data sizes and ranges of process counts, and how many, take into account how many processes are there in a node versus how many nodes you're running. So there's actually a lot of variables involved in a collective communication, and choosing the optimal algorithm for every single case is actually quite hard. So, although MPI implementations do try quite hard to optimize their collectives, they don't necessarily come up with a good solution in all cases. So there can be, and it's hard to do for some operations. So things like all-to-all V, where every process communicates a different amount of data to every other process, is actually quite hard to optimize well. So there can be cases where MPI and OpenMP transfers less data. Okay, so for example, you might be a situation where you have an all reduce, where every thread contributes to the sum, and then every MPI, you do an all reduce across MPI processes, but only once you've received once the MPI is finished, then maybe only the master thread uses the result. So you kind of miss out one of the stages. You can miss out one of the stages of communication where you don't need to distribute the result across all the cores in the node, which was what would happen if you had MPI everywhere. Okay, just to illustrate this is an example from weather forecasting code. So this is the IFS, Integrated Forecast System, is the forecast and climate code that's maintained and used by the European Centre for Medium Range Weather Forecasting. So it uses, and if you don't understand the terminology, don't worry. Okay, it uses a numerical technique for solving the fluid dynamics part of the problem, called semi-Lagrangian advection. Okay, and it's a numerical scheme for CFD, but it has this property where you require data from neighboring grid cells only in an upwind direction. Okay, so it means that only if the wind is blowing from one grid cell to another do you actually need to communicate any data. But that means that you don't know. Okay, so you don't know what data your neighboring processes are going to need, because you can't easily examine the wind field on your neighboring processes. So the MPI solution is that you communicate all the data to the neighboring process that could possibly be needed, regardless of what the wind velocity is on your neighboring processor. Whereas with MPI and OpenMP, at least as long as you're within a node, okay, or within an MPI process, you're only going to read the data from another thread's grid point if it's actually required. Okay, so that's very natural. You just you're basically just instead of having a two-sided communication process, between threads, it's just a question of one thread writing and another thread reading. So it's easy to arrange that. Very naturally, the threads will only access the data that they need. And this results for this particular application code, this results in a significant reduction in communication costs. Okay, so just to illustrate what's going on here. Okay, so weather forecasting operates on basically 2D decompositions. So yeah, the atmosphere is three-dimensional, but because of there are lots of dependencies in the vertical direction, so you typically don't try and to parallelize the vertical dimension in weather forecasting. So the domain is basically two-dimensional. It's a three-dimensional domain, but you only use a two-dimensional decomposition across the surface of the Earth. So it's a kind of sketch of what's going on here. So suppose these are the different domains that are being processed by different processors, and okay, so for the one in the middle that you're interested in, this might be the at this particular point in the simulation, these might be the wind velocity vectors. Okay, so it turns out on this particular time step, the data that's going to be required from neighboring processors are the ones where the wind's blowing in this direction. So that might, for example, just be the green data points would be the ones that you would need from neighboring processors. But we don't know what the wind field is. Okay, so this processor down here can't know what the wind field is in here. So effectively, the simple solution is that, well, you just communicate everything. So you just communicate everything that could possibly be needed. So it will communicate not just the green points, but all the purple ones as well on every time step, just to make sure that all the data that could possibly be needed is communicated. Okay. So by and that. Because you also got deep. This also involves deep halos, so more than one grid point. So the communication costs are quite expensive, but it means that by going to hybrid MPI and OpenMP, then you greatly, you basically increase the domain sizes. You decrease the amount of halo data that has to be communicated, and this type of code actually benefits quite well. Okay, you can also imagine that similar things happen with particle codes as well, where you end up communicating all the particles within a certain radius of the boundary of your local domain, regardless of whether those particles are actually interacting with anything on the neighboring process. Okay, any questions so far? Okay, so those are the potential ways we might gain. What are the problems going to be? Well, I'm going to cover some different topics here. So the development and maintenance costs for the code, portability issues, problems with libraries, and then spend more time looking at the potential performance pitfalls here. What can go wrong? So in terms of development and maintenance, in most cases, it's just going to make your life more difficult. Okay, it's going to make your code harder to develop and maintain than a pure MPI code. OpenMP programming is, in general, easier than MPI, but it's still parallel programming. It's still hard, and application developers need yet another skill set. And also, OpenMP, as with all threaded programming, has the potential for race conditions, non-deterministic bugs. So it means that it makes your correctness testing potentially more difficult. Okay. What about portability? Well, it's not too bad, really. So both OpenMP and MPI are themselves highly portable across implementations. Obviously, nothing's ever quite perfect, but you have a very good chance that if you write an MPI plus OpenMP application, then changing the MPI library and changing the OpenMP compiler, is a good chance that things are still going to work. The combination is slightly less portable. This is not too bad these days. The main issue is what you can assume about the thread safety of MPI. If you assume the maximum level of thread safety, so that it's okay for multiple OpenMP threads to be calling MPI at the same time, then that might reduce the number of MPI libraries that actually support that, or at least ones that support it efficiently. So if you do that, then your portability might be reduced, and certainly your performance portability might be difficult to achieve. So it's probably desirable, at least, to use the features in OpenMP that allow you to, possibly with conditional compilation, to make sure that the code will also still function correctly as a standalone MPI code. And maybe in some cases as a standalone OpenMP code as well. So ability to might be useful in some cases to say, okay, let's just turn off all the MPI and run it as a pure OpenMP simulation. Libraries can be a problem. Okay, if your code relies heavily on libraries in performance critical parts of the code, then you might be in problems. Okay, because if the pure MPI code uses a distributed memory library, then you would need to replace that with a hybrid version, which may or may not exist. If the pure MPI code uses a sequential library, then you might need to replace this with either a threaded version of the library, which gets called from the master thread with respect to OpenMP, or a thread-safe version of the library that gets called from multiple threads inside parallel regions. And again, the threaded version of the library or thread-safe version of the library that you're interested in might not exist. The other problem that you can run into is that threaded or hybrid library versions, if they're based on something other than OpenMP threads internally, you can in some cases run into problems with oversubscription, because what can happen is both your application, which is going to create OpenMP threads, and the library, which is going to create some other sort of threads, maybe POSIX threads or C++ threads on its own, and not just reuse your OpenMP threads, then that might not, and if you're unlucky, they may not behave nicely when not being used. They might not idle nicely. So you can end up in situations where you have, basically you end up with more threads than cores, and your performance can suffer from that. Okay, so what about performance? What can go wrong with performance? Okay, well, several things. Adding OpenMP can introduce additional overheads which weren't there in the MPI code. So things like synchronization, particularly barrier synchronization, problems like false sharing, which we looked at yesterday, potentially sequential sections of code, at least sequential with respect to the OpenMP part of the program, or you can run into the new type of NUMA effects that we also talked about yesterday. So adding OpenMP also introduces another tunable parameter. So you now have to choose, when you run the code, what the balance is between MPI processes and OpenMP threads. So you have to choose how many threads per MPI process you're going to run. And it's maybe difficult to actually determine the optimal value without a lot of extensive testing, because that's going to depend on the hardware that you're running on, depend on the compiler, probably also depends on which MPI library you're using, and then obviously may also depend on your input data as well. So it can be really hard to choose the optimal value of threads per process without extensive experiments. And the other thing you start having to worry about, so hopefully your batch system takes care of it, depending on how well it's been set up. But if you're just running pure MPI, then for the most part you don't care within a node. You don't care which MPI process is running on which core. Simply, it doesn't really matter. At least not very much. There are some modern hardware. There are some effects where it does matter, and it kind of interacts a bit with the way that, for example, the way that collective communications are implemented. So it's not necessarily true to say you completely don't care. But as soon as you're running MPI and process and threads, then the placement really does matter. Okay, so you really want your OpenMP threads all to be running in the same socket or same NUMA domain, for example, as their parent MPI process. So ensuring that can be difficult if your batch system isn't correctly set up to handle it. Okay, so what other things can go wrong? Well, as I said before, it's relatively easy to take a straightforward loop-by-loop approach to adding OpenMP, but it can be hard to get sufficient parallel coverage. So that's really just an expression of Amdahl's law inside a node. So whereas with MPI, you basically you're running MPI processes on every core, and you've written your MPI code sensibly, then your MPI processes are busy all the time, and so your cores are busy all the time. You go to MPI and OpenMP, you might have programmed some parallel loops, but there are also bits of sequential code in the OpenMP bit, so that means that some of your cores are going to be idle some of the time, and that's kind of a little bit harder to avoid with OpenMP without working a bit hard on the implementation. Okay, what else can go wrong? Well, the mixed implementation may end up requiring more synchronization than either a pure OpenMP version was. Particularly if we assume that the MPI is not thread safe, and that's generally what we have to do. Okay, assuming thread safety of MPI is, as we'll come and talk about later, is generally doesn't work terribly well. What also happens is that a lot of synchronization in MPI programs is implicit synchronization through exchange of messages. So MPI processes, a lot of the time, the way they synchronize each other is actually by waiting for waiting for communicating processes to send something. Okay, so you either have, say, a blocking receive call in MPI, or you have if you're using asynchronous MPI calls, using non-blocking ones rather, then you're calling MPI wait or wait all somewhere. Okay, and that essentially forms that's how the MPI processes are synchronizing. So that's very much for point-to-point communication in MPI, that's very much a point-to-point synchronization model. Whereas that's actually difficult to do with OpenMP threads. So this kind of loose one thread to one thread synchronization isn't well supported in OpenMP. So what you typically end up with is barriers instead. Okay, you synchronize all your OpenMP threads rather than having one OpenMP thread wait explicitly for one other thread to do something. Other problem is that if you write pure MPI code and you have a phase, you might have a phase where all your processes are communicating with each other. Then in a clustered system, what's happening is that some of those messages between MPI processes will be going between different nodes, and some of the messages will be between MPI processes on the same node. But very naturally, all those messages are in flight, can be in flight at the same time. Whereas it turns out that it's actually harder if you're to overlap communication between threads, so via the cache coherency mechanism or via reason writes to memory. It's hard to overlap that with internode messages, and I'll come back and explain why that is a bit later on. Okay, and then OpenMP codes can also suffer from this false sharing problem. Okay, which you will basically never see in MPI because every process is operating on an entirely different set of memory. So there's no way that two MPI processes can be accessing the same cache block. Okay, basically covered this yesterday and talked about NUMA effects. Okay, so yeah, of this problem where you've got multiple physical pieces of main memory, and the default policy is for memory to be allocated in the NUMA domain where the first read or write comes from. So yeah, that's clearly the right thing for pure MPI, but it's potentially bad for OpenMP if we haven't parallelized our data initialization. So what that means in practice usually is that the NUMA effect will limit the scalability of OpenMP, and in almost all cases, it's advantageous to run at least one MPI process per NUMA domain rather than one MPI process per node. Okay, so for example, on ARCHER2, okay, every node has 2 sockets. Each socket has 4 NUMA domains. So it's almost always the case that if you're running hybrid MPI and OpenMP, then you want to have at least 8 MPI processes per node, in which case they would be each running 16 threads. So you're probably almost never going to get optimal performance by running fewer than 8 MPI processes per node, and it may be the optimum may be more. Okay, so you may actually very often the optimum value of threads per process often turns out to be maybe 4 or 8 is quite common. Quite often ends up being 4 because of the level 3 cache structure. Because on ARCHER2, because you've got these level 3 caches shared between groups of 4 cores, so it often turns out to be the optimum number of threads per process turns out to be 4, which is partly because of that structure in the memory hierarchy. Okay. Yep. Talked a little bit about this process and thread placement. Okay, so on NUMA nodes, you need to make sure that your MPI processes are spread out across the sockets or NUMA domains, and that the OpenMP threads are on the same socket or NUMA domain as their parent process. As I say, not all batch systems necessarily do a good job of this. Okay, the one on ARCHER2 is actually set up correctly to do that. And it gets even more complicated if you want to use SMT or hyperthreads. Okay, so it's figuring out what the right invocation is to get the right mapping can be quite difficult. And the way that batch systems like Slurm, for example, describe these things can be extremely confusing, and the documentation isn't that good, unfortunately. Okay, so I'm going to move on and think about the different styles of writing MPI and OpenMP together. So essentially, we can identify 4 different ways of doing this, and the differences come from the differences in when and how OpenMP threads are permitted to make the MPI library calls. And each of these has advantages and disadvantages. And then we'll also look at MPI's threading interface. So it allows us to request and also to query the level of thread support which the MPI implementation provides. Okay, so the 4 styles are described here, and I will go into more detail about them afterwards. So the names that have been sort of applied to them are, first one is called master only. So this is the situation where all MPI communication takes place in the sequential part of the OpenMP program. So in other words, you never have any MPI calls inside parallel regions. And that is the most commonly used pattern for implementing MPI and OpenMP because it's easy. And we'll also see why that's the case in a minute. But it doesn't necessarily guarantee you the best performance. Second one is funneled, where we guarantee that all MPI communication will take place through the same thread, the master thread, the OpenMP master thread, but that communication could also come from inside parallel regions. It could come from thread 0 inside parallel regions. The third one is called serialized. So this is where we do allow different threads inside parallel regions to make MPI calls, but we guarantee that only one thread at a time is going to do it. We now have some problems with how do we, as soon as we start allowing multiple threads to communicate, then we have to invent some mechanisms to distinguish sending and receiving threads, okay, to try and make sure that messages end up in the being received by the correct thread. I'll talk a little bit about how that's done later on. So either use MPI tags or communicators to do it, which is a bit messy. Okay, and now we start having to care about race conditions on MPI buffers and so on. Okay, and then the final possibility is multiple. So this is where we allow threads to call MPI simultaneously. So MPI communication can happen simultaneously in more than one thread. Some MPI implementations don't support this. The main ones, things which are based on MPitch or OpenMPI or their derivatives, mostly do support this. However, they don't necessarily perform very well because it forces the MPI code to take care of synchronization internally to avoid any potential race conditions or anything bad happening if multiple threads are accessing the internal data structures inside the MPI library. Okay, so it's the sketch of the different styles here. So master only would be okay. So where you have parallel regions where you just do computation and all the MPI calls happen outside of parallel regions on the master thread. Okay. So funneled would look something like this. Okay, so you can have inside a parallel region, all threads might do some work. You might need to synchronize the threads, and then the master thread does the MPI calls, at which point you might need to synchronize again so that threads know that the other threads know that the MPI calls have completed, and then do some computation. So serialized, well, there's quite a lot of different ways to implement serialized, but one way would be example for inside a parallel region to wrap all the MPI calls inside a critical construct to make sure there's only one thread at a time calls MPI. There are a number of other possibilities of how to arrange that. And then for multiple, well, anything goes. Okay, so it's possible for threads to call the MPI library at the same time from different threads with no restrictions. So said a little bit about thread safety. Okay, yeah, I've already hinted about this, that making the MPI libraries thread safe is actually difficult. The internals of MPI libraries are really quite complicated, and there's a lot of legacy code in there. And so the main MPI library code bases were developed originally before anybody thought about thread safety, and retrofitting thread safety into them efficiently is quite difficult. You can imagine you either have to lock access to internal data structures, or you have to replicate them, replicate the data structures one per thread. And so this can add some significant overheads, which may affect normal MPI, normal single-threaded MPI codes. So in order to deal with this, MPI defines various classes of thread usage. And then the library is allowed to supply an appropriate implementation depending on what we as programmers ask for. So the way MPI does this is via the MPI init thread routine. So this does the same thing as MPI init. So it's the routine that you have to call at the start of the MPI program before you call anything else. So what you do if you're going to use threads, you are supposed to call MPI init thread instead of MPI init. And it has these two additional integer arguments, which are the required level, okay, which is an input. It says that's the level of desired thread support that we want, and then it returns as an output argument the provided, so the level of thread support that the library is actually going to provide for you. Okay, so it has these extra extra parameters that you have to pass. Okay, so the values that these parameters can take are also predefined constants in the MPI library. So there's 4 possible values. Okay, first one is MPI thread single, which guarantees that there aren't going to be any additional threads. Okay, only one thread is going to execute. Funneled. Okay, so the process may be multi-threaded, but only the main thread is going to make MPI calls. So that covers both the master only and funneled OpenMP patterns, if you like. And then thread serialize, okay, maps to serialized pattern. Says the process may be multi-threaded, and multiple threads may make MPI calls, but only one at a time. And then finally, MPI thread multiple, which says, anything goes. Multiple threads can call MPI with no restrictions. Okay. So these are constants defined in the MPI library, and they are guaranteed to have monotonic increasing, strictly increasing values. Okay, so you can compare them. Okay, so they don't quite necessarily strictly map onto the 4 mixed mode styles that I've described, because they're intended to be somewhat more general than just OpenMP. Okay, so they're intended to work with things like POSIX threads, where you don't have concept of parallel regions, for example. And then there's also just a query function. Okay, so you can just query the provided value at any point in the MPI code. You don't have to don't have to do it just at the MPI init stage. Okay, but so it allows you to have sort of defensive programming kind of style. Okay, so if the provided if the value that's provided is less than what you asked for, then you can take some suitable avoiding action, like terminate the program because it might not work correctly. Okay, so let's think about these different styles of writing mixed code and what the advantages and disadvantages are. Okay, so for master only, the advantages and the big advantage is that it's relatively simple to write and maintain, because you have a clear separation between the different levels of parallelism. So outer level expressed with MPI and your inner level expressed with OpenMP, and they don't interact with each other at least in a sense of how the program is written. And also, you don't have any concerns about synchronizing threads before or after sending messages, because all the messages come from outside parallel regions. The downside is that are several. It basically means that while the MPI calls are happening, the threads that other than the master thread can't do anything. Okay. So you end up with, while the MPI calls are happening, the other cores in your that the threads could potentially run on are sitting there doing nothing, and that turns out to fairly strongly limit the number of threads that you can use with this style, because what tends to happen is that as you reduce the number of MPI processes, you end up sending longer messages per process. Okay, you might end up communicating less data overall, but the messages that each process has to send and receive get bigger. Okay, so for example, just because if it's for Halo exchanges, the local domain size is bigger, or for collective communications, the amount of local data that you're sending gets bigger. Okay, so that tends to, so there's kind of double whammy, it's kind of a double effect there. So not only as you add, as you go to more MPI threads per process, suppose you're keeping the total number of cores constant, then what happens is the time spent in MPI calls gets longer, and then the consequent idle time also gets longer, because you're adding more threads. There are more threads sitting there doing nothing while the MPI is happening. So you kind of get this sort of multiplying effect. So the amount of idle time tends to increase quite substantially as you add more threads. So that's probably the main one that will limit the performance, limit the optimal number of threads per process really quite small numbers, probably around 2 or 4, very typically. Other problems, okay. Well, all the data that gets communicated has to pass through the cache where the master thread is executing. Okay, so whenever you communicate data, that implies that the core is doing loads and is loading or storing that data, okay, from memory. So everything has to go through. Well, everything will get copied into the cache where the master thread is executing. The problem is that, as we'll see in a minute, inter-process and inter-thread communication don't overlap with each other, okay? Because the inter-process communication is happening outside parallel regions, the inter-thread communication is happening inside parallel regions, and those two things are not happening at the same time. The only mechanism we have for synchronizing threads between calls to the MPI library is parallel regions, which has relatively high overhead. And the other problem that we run into is that if we are using derived data types in MPI, then it's only possible for any packing and unpacking of those data types is being done inside the MPI library calls, and that can only be done by that's happening one thread at a time. So you might think, oh well, that doesn't really matter very much, but it turns out that if you are packing and unpacking non-contiguous data, then that consumes a lot of memory bandwidth. You get bad cache behavior, and in fact, it turns out that the packing and unpacking can be of the same order of magnitude as the actual cost of sending the messages. So that's bad. Okay, so let's have a very, very minimal program, MPI program. Okay, so this is basically it's a one-sided Halo exchange, and it exchanges exactly one element of an array. Okay, so the first loop here computes values of A. And then basically each process is going to send AN to its neighbor and receive send from AN and receive one word into A0. Okay, and then do something with that involves or the rest of A. Okay, going to compute with A again. Okay, so let's turn that into a hybrid program by adding the OpenMP directives, just OP parallel do to each of the loops. Okay, but okay, let's make sure that we keep we're going to keep the global problem size constant. Okay, so what effectively that means doing is that the length of the loops that each MPI process is going to do is going to increase by the number of threads. Okay, and same down here. Okay, so in order to keep the amount of work done per core constant, then we need to increase the size of these loops by the number of threads. Okay, so you wouldn't really write code you wouldn't necessarily write code like this in practice, but this is just to illustrate, to make clear what's going on here. Okay, that the length of the loops is changing. Okay. So what goes wrong here? Well, what additional costs are we incurring? Well, we're adding a barrier synchronization point here at the end of the parallel region. Okay. And so every thread has to wait for every other thread at this point. Okay. Whereas with all the MPI synchronization is doing is that we've got one process waiting for one other process in the receive. So we're basically adding additional. There's additional synchronization going on with the OpenMP that wasn't present in the MPI program. So have the MPI messages, as I said before. Okay, so some of these messages will be between MPI processes on the same node, so that's the intranode messages, and some will be between MPI processes on different nodes, those are the internode messages, and those naturally happen at the same time. But okay, where does the inter-thread communicate? Where does the corresponding inter-thread communication? Well, it occurs here. Okay, it occurs here because for some values of I, so particularly because it's accessing I minus 1 here. So for some values of I, the thread that's reading this element of A is not the same thread that wrote it up here. Okay, so you'll get some cache misses in this loop here, which are effectively doing the inter-thread communication. Okay, but the cost of that appears in this loop here, and it is not happening at the same time as the message passing. Okay. So what happens if we move to a funneled approach? So it's now still relatively simple to write and maintain. It's a little bit more difficult. We might need to restructure the code in some ways to be able to call to do MPI calls inside parallel regions. So that might be might require some code refactoring to be able to do that. There's now essentially somewhat cheaper ways to synchronize threads before and after message transfers, because we don't have to shut down the parallel region and start a new one. But it's now possible for other threads to compute while the master thread's in an MPI call. Okay, so this gives us the opportunity, an opportunity to overlap, explicitly overlap communication and computation. Which might be a good thing. Okay, so it's possible we can now we're not forced to have idle threads while the MPI is happening. Okay, so you might think, okay, well, can I not just? I mean, even in the master only version, can I not just use non-blocking MPI calls and get the overlapping to happen anyway? Can I not do I sends and I receives and then go off and do a parallel region and do some computation while the MPI is happening, and then call MPI wait or wait all after the parallel region? The answer is, well, yes, you can, but in practice that really doesn't work. Okay, you don't actually get any overlapping. The reason for that is that the MPI library typically can't really make any progress while the code isn't in the MPI library. So what you typically, although you can write code like that, you typically find that you don't actually get any overlapping in practice, or very little, and that it simply all it does is it delays the actual message transfers until the point where the wait is called. So non-blocking MPI communications really don't in practice manage to achieve much overlapping, whereas with funneled you can do it explicitly. You can have one thread doing the MPI calls, all the other threads explicitly doing computation at the same time. Downsides. Okay, there is now a less clear separation between the levels of parallelism. We still have the locality problem with the messages. Okay, we've only got one, so all the message data gets shoveled through the cache where the master thread is executing. We maybe still didn't manage to overlap into processes and into thread communication, and we've introduced this kind of awkward asymmetry between threads. Okay, so by having having to mark out the master thread as special because it's the only one that can do the MPI calls, we end up with this kind of slight awkwardness. Okay. So if you want to try and do overlapping, there's a couple of options here. Okay, so for example, you might have a pattern that looks something like this. So inside a parallel region, all the threads do some computation. they synchronize with each other, and then you say, okay, well, if thread number is 0, then do the MPI calls. Otherwise, go and do some computation. Okay? And that's okay, but the unfortunate thing about that is that in this else branch here, we can't use work sharing directives. So you can't do parallel loops with OpenMP 4 or OpenMP do inside this else branch, because of the restriction that all the threads in the parallel region must encounter the work sharing directives. So that's pretty nasty, okay? At least for if you've got loops inside here, then you'd have to schedule them manually rather than using work sharing. Tasks, yeah, tasks would work. That would be a possibility. Tasks have overheads. You also lose any ability to. You also lose data affinity with tasks. You're basically losing control over which threads are doing what computation. So yeah, task is a possibility, but it also has its downsides. The other way to do that would be to use nested parallel regions. Yeah, so it would be create an outer parallel region with 2 threads, and then if from those 2 threads, you pick one of those threads to do the MPI calls, and then the other thread spawns a nested parallel region to do the computation. So this would be another way of doing it, and then at least you can use work sharing in here. So that might be from coding point of view, might be a nicer way to do it, but it has higher overheads, and also you can't, there's no way of synchronizing between these branches. Okay, so you can't easily synchronize between this code in this branch here and code that's inside the parallel region in the else branch. But maybe that doesn't matter, okay? If you're doing overlapping anyway, then it kind of implies that there is some computation that's completely independent of the MPI message passing. So maybe that doesn't matter too much in some cases. And what about serialized? Okay. Well, this now makes it easier in some senses for other threads to compute while one's in an MPI call. And we kind of lost this. We no longer have this sort of asymmetry problem. We don't have to have a special communication thread that we have to with funneled. Okay. And you can also you also think, well, now I can have better locality, because you can arrange for threads to communicate, to essentially communicate the data that they've computed, if you like. Okay, so I know threads don't really own data, but you can get better locality by arranging for a thread that's going to send and receive some data is also going to be the thread that does the computations using that data. Downsides, okay. Well, this is getting certainly harder and to write or maintain. You end up, if you're splitting up the messages between threads, you're going to be sending more and smaller messages, and so you're going to get some additional latency overheads in the MPI. And then we also have this problem now, because we've got multiple threads potentially sending and receiving messages, need to use tags or communicators to distinguish between the messages from different threads in the same MPI process. Okay. So yeah, this is a bit ugly, okay, because MPI doesn't know anything about threads. So a call to MPI received by any thread in an MPI process is going to match an incoming message from the sender. So MPI will also do matching in order. Okay, so the first receive call will match. The first receive call will happen will match the first send that happened on the other side. But nevertheless, okay, we still need to be able to distinguish between different threads to make sure that the messages end up on the right thread. Okay. So we can use tags for the MPI tags for that. So there's a tag field in the MPI call, which ensures that only messages with matching tags can be. You can only receive a message that's been sent with the matching tag. But if you already, people use tags for other things as well, and there's only one. You only get one integer worth of tag. So if you're already using that for other purposes, that gets messy. You start having to encode the tag that you already had and the thread ID back into one integer, and take care that the values never overlap and you don't run out of tag fields, which is some MPI implementations don't really have quite as many tags as you might think available. So it can be a bit messy. Make sure that it all works okay. The other option would be for different threads to use different MPI communicators. Okay, and that will work for some simple patterns. Where, for example, if thread n in one process only ever communicates with thread n in another process, then or in other processes, then all the thread ends can use a different communicator. Can use a separate communicator. But more complicated patterns will get messy. So even just simple halo exchanges get very messy to try and handle with multiple communicators. Okay, and then finally multiple. So the advantage here is that at least in theory, the messages sent and received by different threads can actually be happening at the same time. But in practice, in order for the MPI implementations to make themselves thread safe, they actually get serialized internally inside the MPI library. So you don't really win from that. It is kind of more natural now for threads to communicate their own data. Okay, it now becomes easier to arrange for the fact that threads are computing and communicating the same bits of data. And now we've actually got fewer concerns about synchronizing threads because we've thrown the responsibility for that over the wall into the MPI library. Downside, yeah, this is kind of hard to write and maintain. There's potentially some loss of portability, and MPI implementations don't actually tend to perform terribly well like this because the thread safety is internally done fairly crudely. Okay. So sum up. Okay. So MPI and OpenMP programming is becoming reasonably standard practice in a lot of applications. I think we did. So wasn't on ARCHER2. This was on the predecessor system, Archer. We did do an exercise to try and estimate how much usage they had, and we came out with a number that was it was a little bit difficult to do it accurately, but we estimated that about 30% of the consumed CPU hours on Archer were coming from hybrid MPI and OpenMP applications. So I don't think we've done the same. We've tried to do the same analysis on ARCHER2, but it would be interesting to see if that number has gone up or down. So yeah, getting it right is difficult. Getting it to perform well is also quite difficult, and have to potentially, you then have to take care of choosing the number of threads per process, and in some cases, if you're to worry about getting the placement of processes and threads on numerous systems correct. Okay. Any questions? Okay, so Ankit asks, how do environment variables like OMP num threads and MPI thread level? Okay, so MPI thread level is not an environment. The thread level is not an environment variable. Okay, at least not the way I've described it. Okay, the levels of the thread levels are arguments to their constants, which are arguments that you pass in or out of the MPI init. OpenMP, so yeah, I mean, typically what you do is, yeah, OpenMP num threads works fine. So you basically you typically set your number of, set OMP num threads before you execute the code, particularly in a batch submission scenario. You just export OMP num threads inside your batch script before running the MPI application. Yeah, that's the number of that's the number of threads per rank. Yeah, absolutely. Yeah. Fortran co-arrays and OpenMP. Anything might happen. I think, if I remember correctly, even the latest versions of OpenMP specification don't say anything about co-arrays. So it might work. Depends on the compiler. Okay, what about the impact of MPI's blocking and non-blocking communications on OpenMP threads scheduling and performance? Okay, so now, as I kind of hinted before, the MPI libraries, for the most part, can only do anything while they're inside MPI calls. Okay, so an MPI library can't make progress in the background because it hasn't got access to. There's no way for it to have access to any CPU resources to do anything. Okay, I mean, this was kind of different a long time ago, when machines were designed differently, and you had explicit communications coprocessors in the machine. So you basically had separate chips that that effectively handled the communications and could run some of the code that was inside MPI. That's no longer the case on modern machines. So the only place that the MPI library can run is on the actual compute cores. So there's the network interface, the NICs, the network interface cards have or interface chips have very limited. There's almost no ability to do any computation on there. Okay, some very minor stuff like computing reductions or something like that is possible, but to first approximation, all the MPI code has to run on the compute CPU cores. So that means that the MPI library can't really do anything unless you make a call to the MPI library. Okay, and in which case, the first thing the MPI library always does is try and make some progress. Okay, so it says, are there outstanding messages that need sending or receiving, and it will try to do something, but then it won't do anything unless you're actually inside the library. Okay. Some MPI implementations have an option which allows the MPI library to create an additional thread or threads to try and make progress. In practice, that often doesn't help very much, and it can also conflict with the OpenMP threads. Okay, because what can happen is that if the MPI has an additional thread, then and you run as many OpenMP threads as you have cores available, then you've got an extra thread somewhere. Okay, it might, if you're lucky, it might get scheduled on a hyperthread, but it's difficult to that might not work. But it's also that thread is going to be, that MPI thread is going to be, if it's sending and receiving messages, it's going to be accessing a lot of data. So it's going to be, it's going to be consuming both CPU resources and cache space and memory bandwidth resources. So that can impact on the performance of the, if you have an MPI helper thread running at the same time as your OpenMP threads, then the performance might not be very good because you've got some conflicts. You're basically oversubscribing your hardware resources. So, I mean, if in that case, one thing you can try to do is you can run you can leave a core spare for that helper thread. So, you might say, okay, I'm going to get my batch system. I'm going to allocate 4 cores per MPI process, but I'm only going to set the number of OpenMP threads to 3. So you could potentially only use 3 of the cores for doing your OpenMP computation, leave a core spare for the MPI helper thread, and kind of hope that it all works out okay. Obviously, there's a risk that you are then reducing there are parts of the program where the MPI helper thread has nothing useful to do, and therefore you're losing a core from which you could be using for the OpenMP computations. Okay, anything else? Okay, so I'm a bit ahead of schedule for a change. So what I suggest is we'll take our break now for half an hour, and then come back and do the next practical session. And I'll also spend a bit of time just talking through the solution to the first set of exercises as well.